Welcome to today's web seminar. Our conversation topic today is Fundamentals of Electrochemical Impedance Spectroscopy and Application to Lithium-ion Batteries. My name is Rob Sides. I'll use the next hour to explain the fundamentals of EIS and the role it plays in supporting research initiatives in electrochemistry. For this audience, we will showcase the practical advantages of energy storage and energy conversion, specifically different challenges at different points in the activity chain for lithium-ion batteries. These include material development, cell characterization, and module evaluation. EIS is a high-value technique, but is often intimidating to users. The specific goal I have for myself and you today is to leave here with a better understanding of EIS and how you can apply it to your studies. I represent the global enterprise AMETEK. Prior to joining AMETEK, I received my PhD in techniques of fabrication and characterization of lithium-ion battery electrodes. I've been with this group for almost 12 years in many different roles and functions, including support, product line management, marketing, sales, and applications. So with my introduction and the scope of today's presentation defined, let me introduce AMETEK. AMETEK is a diverse manufacturer with sales in 2019 of $5.2 billion. My location is here in Oak Ridge, Tennessee, in the USA. With my colleagues, we make up the Advanced Measurement Technology Business Unit. With AMETEK, we have the support and backing of a large corporation, and the reliability and diversification of AMETEK helps identify solutions to the most complicated problems. Now, take a minute here also and look at the way we interact with our regional and local customers. The orange is where we cover the globe with direct sales, and blue is where we go to market through our channel partners or distribution. I'm pleased to announce that recently we have decided to take a direct approach to customer interfaces in the UK and Nordic regions, as well as the DACH territories. So we've expanded our position in Europe. Our two brands that serve the field of electrochemistry are Princeton Applied Research and Solartron Analytical. PAR was founded in 1961 as the innovator of the digital potentiostat. In today's presentation, you'll see data both from our single-channel Versastat series, as well as the modular multi-channel PARStat MC, maybe our Versascan as time permits. Solartron was founded in 1948 as the innovator of the frequency response analyzer, the FRA. We'll discuss how an FRA facilitates electrochemical impedance spectroscopy measurements. In today's presentation, you'll see data from our single-channel Energy Lab XM, as well as our battery analyzer, the SI9300R. We'll be talking a lot today about the fundamentals and tests and instrumentation. I do encourage you, when you're looking for a company to partner with, you consider all aspects of value and support. And this is what I refer to here as the AMETEK advantage. We have a knowledgeable global team that includes a value-add sales network, trained local technicians, PhD-trained scientists, as well as you, the global community of researchers that develop and share best practices for experiments and analysis. We have tools and solutions to support the three broad fields of electrochemistry and materials research. We segment electrochemistry into three areas of energy, corrosion, and physical electrochemistry. EIS benefits each of these key application areas of electrochemistry. Within energy, we have the subsegment or application areas of batteries, capacitors, fuel cells, and solar technology. We'll use EIS in studying diffusion at the material development level, all the way through state of charge and state of health measurements with lithium-ion batteries. For corrosion, EIS is the technique that identifies failures in paints or coatings that serve as barriers to corrosion. Many sensors are based on methods of monitoring a changing impedance response, and this may be for analytes such as tuberculosis or ozone. We also support an adjacent market that we refer to as materials. Here, the impedance at changing temperatures measures conductivity or permittivity of materials such as dielectrics or ceramics. So I want to lay the groundwork and define some DC and AC techniques, and then we can compare them. So when we say thermodynamics or driving force or polarization, we mean potential or voltage, and we're going to use those terms interchangeably. This describes if a reaction is going to happen. When we say kinetics or rate, we mean current, and that describes how fast a reaction will happen. So let's start with let's open the discussion with that of the open circuit potential. Open circuit potential is a potential that develops at any electrode-electrolyte interface. There's no net or no measurable current flowing at this point. Therefore, we only have that thermodynamic information, not kinetic information. When we connect a potentiostat or battery analyzer and measure the open circuit voltage, we're measuring it in similar fashion as a voltmeter would. Then we use these instruments to drive reactions of interest through voltage control and gain valuable kinetic information through current measurement. There are three different types of signals that can be used to accomplish this. One is the DC bias or offset, and this is used for a constant voltage experiment. It's often referred to as potentiostatic or coronal amperometry experiment. Then we have a ramp type, and that's used for any experiment where the voltage is swept at a defined rate. The most popular of this type of experiment is a cyclic voltammetry experiment. Any experiment whose signal is comprised of either a DC bias or ramp or a combination of these two is considered a DC method, or sometimes referred to as a time domain method. The resulting current from a DC method is going to be the sum of all the processes, so those related to charge transfer and those related to charge storage. Also, this imposed controlled potential signal may irreversibly change the system. We'll talk about that later as well. The third signal type is a sine wave, which is an AC wave. And there's two pieces of information that we need to construct a sine wave. Its magnitude and its frequency. Because of this frequency component, we may refer to this as frequency domain. This is the primary signal type that we'll use for EIS measurements. We will use an EIS of a fixed magnitude and increment the frequency. The magnitude is much smaller than typically employed with DC experiments, and we'll cover the why and the associated benefits throughout the presentation. I increment this frequency because there's a frequency dependence on the impedance of electrochemical cells. And by changing the frequency, I'm using that as my tool to probe different electrochemical processes and thus separate the contributions of each to that of the total response. Above all, this is the additional information that drives researchers to EIS. In DC experiments, all electrons look and act the same. So go back to the primary equations and primary concepts we learned in our introduction to electrochemical theory or even electrical theory. We started at Ohm's law. Ohm's law defines the relationship between voltage and current, the ratio of which is the resistance. Now for AC methods, we're going to just turn that resistance into a more general term of impedance, represented here and commonly as Z. The relationship is similar, but it still defines the relationship between voltage and current. The term is more general as it includes any reason why current is not flowing in the cell. This could be resistance or capacitance or inductance or diffusion. We're going to talk about each one of these in the next several following slides. So let's refer to this now as signal and response and not necessarily as voltage or current. But the graph here shows an AC signal here labeled E in black and the measured response here labeled I in red. And because of their relationship, they match type, which means AC wave goes in and AC wave comes out and they match frequency. However, they probably differ in the other two traits, their relative magnitude and their relative phase. The ratio and magnitude of those two waves is one component we will use to characterize the impedance. And the other component that is used is called phase shift. Phase is the difference or offset between those two waves. So think about cosine response having a 90 degrees phase shift versus a sine response. You'll hear this referred to as the current leads or lags of voltage as they're separated by some Greek letter, and sometimes you'll hear it referred to as theta or sometimes you'll hear it referred to as phi. But phase is a key component in the data analysis of EIS, that offset in phase. Here we're also going to define omega, and it's just the angular frequency or 2 pi f. Just as we started with the common Ohm's law and adapted it for EIS, let's return to another key equation or relationship in electrochemical theory, the Butler-Volmer equation. This relationship describes linearity of systems. Butler-Volmer describes the kinetics also and kind of how fast reactions happen. So if you're an equation person, look to the left. If you're a graphics person, look to the right. But in general, it defines this relationship of current, here I, to potential or over potential, represented here as eta. But now when we have the over potential is small, we can ignore some terms through the Taylor expansion series, and it's going to simplify and reduce. And the importance here is that the condition of a small over potential, the current varies linearly with potential. In this graph on the right, in the range right around the open circuit voltage, if I apply a small voltage and get a current back, it's going to have a small relationship. However, if I drove a very large voltage, you can see this relationship would become nonlinear. So what's the significance of this? The relationship really tells me that the small voltage, whether it be AC or DC voltage, I can gain information on electrokinetics. However, if I'm applying just a small voltage in a DC experiment, I'm not going to get all that information about mass transport or diffusion. That information is held at large potentials for DC experiments. As you see the cyclotherapy experiment, I got to drive to that very far extreme potentials so that I'm governed by mass transport instead of kinetics. The AC-based method of EIS, however, is applied the wave across a wide frequency range. And by doing that, I capture information on electrokinetics at high frequency and diffusion or mass transport at the lower frequencies, so both in that single experiment and by only applying a small stimulus. And we know, in particular for this application at a material development point in the activity chain, how important diffusion is to the performance of lithium-ion batteries through its intercalation process. So there are conditions or expectations to be met for valid EIS experiments. First, the system should be stable. Stability refers to the amount of drift in the system. The duration of EIS experiments is really driven by how low the frequency is being measured, but data point density or points per decade also plays a role in this. But you may see scatter and impedance data at the lowest frequencies. In particular samples of low or medium impedance magnitude, this may be due to a lack of stability. At high impedance samples, may show scatter. It may also show scatter at low frequency data, but that's common to other issues with measuring low currents, specifically the resolution of the measurement itself or environmental noise. So let's just think very simply that frequency is 1 over time. So take the example of a single data point at 1 millihertz. It can take almost 20 minutes per cycle. And EIS may take more than 1 cycle per frequency to improve data quality. In our systems, this is called data quality, or it's called integration period. Or additional cycles or delays may be required to allow settling time for any changes in the current ranges or filters or gains that the algorithm dictates. And remember, mass transport data, such as solid state diffusion within the lithium-ion battery electrode, happens at low frequencies. We need to study EIS at low frequencies, so techniques such as viewing data of a given frequency on an E versus I graph in a time domain may help you visualize drift. This is shown here as the cycles of repeat on a single frequency. Also, the speed at which what we call new technology or speed through technology with our PMC 200, and you'll see an aggregate time of EIS experiments, and it is not unusual at all to be able to measure down to let's say 1 hertz in less than 10, substantially less than 10 seconds, and 100 millihertz in less than 80 seconds total test time. The second condition is that of linearity. As we discussed in the Butler-Volmer slide, when you see this written as if the signal of A gives a response of B, then a signal of 2A gives a response of 2B. And so the significance of this is that we can adjust the size of our signal without changing the measured response, because the ratio of the relationship is what we're interested in, and that ratio is not changed. We'll speak further about best practices or recommendations and tools available for the selection of amplitude of EIS at the end of today's presentation. The last point here is causality. So think about causality like cause and effect, and simply the response is due to the signal being applied. So we've got some examples here. You know, if you are measuring down to milliohm samples or microohm samples, you've really got to consider every single piece of your system, and this includes connections and cables. So by conforming to these, we can say our EIS measurement is valid. but also it means that you can characterize it as being non-destructive because I've not changed the response by applying this EIS step. There's also a mathematical transform and Kronig relationship, the goal of which is to determine mathematically the validity of these measurements. So why is frequency important? We stated here earlier that frequency is my tool, my toolbox that's going to allow me to apply a small signal and probe both high and frequency and data for fast electron kinetics and low frequency data for slow processes such as diffusion. But frequency does another thing for me as well. Yes, it's going to lay the framework for my data analysis, and that's because there are electrical components that have defined relationships between frequency and their impedance and their value. The first one we'll cover is the most simple one mathematically. It's the resistor. The impedance measured in ohms of resistor is simply the value of the resistor itself. The equation is thus Z equals R, and note specifically that the parameter frequency is not present in that equation. So the impedance of a resistor is independent of the frequency being applied. So now let's discuss the impedance of a capacitor. The equation does have a frequency component. Remember, we defined omega as 2 pi f, and so what this tells me is the impedance of a given capacitor is high when we're at low frequency, and it's low when we're at high frequency. That is referred to as an inverse relationship. The next component is that of an inductor. The impedance of an inductor also has a frequency dependence, but it's a direct relationship, meaning that the impedance of an inductor is high when measured at high frequency, and the impedance of the inductor is low when measured at low frequency. Over the next 4 slides, I'm going to take each one of these common components using equivalent circuit analysis and delve into examples of where you would see them in different types of electrochemical cells representing different physical or chemical processes. And notice I said 4 slides because we're going to include diffusion. So in the same order, let's go through and first cover resistance and the resistor. So let's examine our system and think about where I see resistance in our electrochemical cell. One example is the solution resistance pictured here. It's the resistance between the working electrode and reference electrode. This exists due to their physical separation in space and is influenced by conductivity of the electrolyte and their size. In energy devices, we refer to equivalent series resistance, or ESR, of which solution resistance is a key part. But it's so low, the solution resistance is so low, and the total impedance is so low that we do need to consider other connections and cables, as we were speaking about earlier. Another example of a process in our system that acts like a resistor is the charge transfer, or sometimes called the polarization resistance. Charge transfer resistance characterizes the electron transfer of the Faraday reaction, the reaction of interest. So for a fast reaction, this resistance is low, and for a slow reaction, this resistance is high. The background is building now for help us create circuits for data analysis. This is one of the steps that users find intimidating. But let's look at the contributions of solution resistance, equivalent series resistance, charge transfer resistance. Just off their names alone, we have a pretty reasonable idea that they're going to act like a resistor and be represented as such. And so there are resistive values, and these examples are going to be modeled by resistors as we build our circuits. Take the relationship of impedance of a resistor and apply it to a 1 kilo ohm resistor. Take this time to really think about what we would expect its impedance to look like and how its impedance acts as we change the frequency during the experiment. Since there's no frequency response dependence on the impedance of the resistor, even though I'm incrementing the frequency, the impedance of that resistor does not change. The magnitude then is just going to be equal to the resistance value, and the phase shift we talk about is 0, and you may hear this as the current and voltage are in phase with each other. So let's now tackle the next component. Let's talk about different sources of capacitances in electrochemical cells. These are some examples of physical or chemical processes that occur in our cells that are traditionally modeled by capacitors. With this first one that comes to mind is the electrochemical double layer. So I've included this graphic on the right for the electrochemical double layer. In the case, this is a new concept for you, and we'll refer to it again in expanded view in the diffusion discussion. Start by considering a generic electrode, and so that's going to be any metal and any electrolyte, and that metal has electrons. All of those electrons have a negative like charge, and that means they want to repel each other. In order to maximize separation, all of these negative charges reside at the surface of the electrode. This principle is referred to as Gauss's law. An electrolyte is typically an electrode a liquid that has a salt dissolved in it. It could be KCl in a traditional electrochemical cell, or something like LiPFS6 in a lithium-ion cell. But the salt is going to dissociate into its cation and anion. For example, the potassium plus and the chloride minus in our KCl example. So we draw the plus sign and the minus sign, but we also don't think about drawing the solution or the liquid. These ions do not exist independently in space, right? They're solvated, or they're surrounded by liquid molecules. So the positive solvated ions arrange themselves preferentially close to the negatively charged ions of the electrode. This creates a system of oppositely charged parallel plates separated by a dielectric, and that's the liquid, and so this is the fundamentals of a parallel plate capacitor. A capacitor stores charge, so no issue or complication. However, when our potentiostat takes control of the cell and imposes a voltage on the electrode, in addition to the charge transfer process, we also get this dis or reorganization of the double layer. This causes a current to flow that's not associated with the reaction itself. So instead of Faraday current, we refer to this as non-Faraday current. A tremendous advantage and application of EIS is to separate Faradaic and non-Faraday current. So how can we do this? And the answer is taking the advantage of the difference in frequency dependence. So let's consider how the impedance of the capacitor changes as I increment the frequency during the course of the experiment. At high frequency, the impedance is low, and at low frequency, as the frequency becomes lower, the impedance becomes higher. So when it draws on a plot, it's going to be a straight line with a slope of -1. On phase shift, it will be represented as 90 degrees. And it's going to be because the current and voltage are out of phase. I'm going to introduce a concept here called the constant phase element, because you'll see this often in literature and used as a replacement for the capacitor to model imperfect or leaky capacitors. CPE have become very popular because, frankly, a model of the CPE element fits the measured data better than the capacitor does. Why is this? A CPE has 2 degrees of freedom, or 2 fit parameters associated with a single element. So there are 2 parameters able to be adjusted, and so you're just going to have a better fit when you're using a CPE element. Also, let me point out this term J in the equation here. This is responsible for what I refer to as the imaginary component of impedance. So please understand this relates to imaginary number principles, as in the square root of -1. But it really exists. It's really impedance, and is a key point to the total overall contribution to the cell. Next, let's discuss the sources of inductance in our electrochemical cell. Inductance is based on the field that is created from current flowing in a loop. This is physics and E cross B relationships and right-hand rules and this kind of things. So traditional electrochemical systems may not see inductance because their impedance at high frequency may swamp out the inductive component. But energy devices have lower impedance and higher current than traditional systems. And I know high frequency because the impedance of the inductor is directly proportional to frequency. So where can I see current flowing in a loop in an energy device? Specifically for lithium-ion cells, let's consider an 18650 cell as a cylindrical form factor. We adopt that cylindrical form factor to increase density, and so we're basically rolling up a flat, virtually 2D system. However, that does create current flowing in the loop, which creates an inductive effect that should be included in the model. Let's consider a different, more general example. As both the current and voltage are measured at the cell, the connections responsible need to be in proximity, so these things need to be close together. This is influenced by positioning for cell cables, their type, such as you have a twisted pair, the complication then is that the inductive field generated by the current carrying leads is picked up by the voltage sensing leads. This can cause measurement artifacts in the data. It's not noise, it's not bad data, it's a consequence of the measurement. And equivalent circuit analysis allows us to quantify that contribution. Current and voltage here are also out of phase by 90 degrees, just with the opposite sign of the capacitor. There's a linear relationship with frequency and slope, and so that slope would be a positive 1 line. There's the invisible positive 1 in the equation. The thought exercise here is to consider how the impedance of a given inductor changes as frequency increments. And you can simply look at the equation, you can see the slope would be +1. The last element of impedance that I want to discuss is diffusion. This is a little bit more difficult to describe with the simple passive electrical components because it's really not an analog version. We can take that picture we showed to describe the electrochemical double layer previously, and let's just keep walking it out and expanding it further. You're going to see the diffuse layer. This layer lives between the electrode interface and the bulk. I described the diffuse layer as the one that is influenced by, but not in direct contact with, the electrode-electrolyte interface. And so in classic mass transport controlled experiments or Nernstian experiments, such as electrochemical sensors, the potentiometers poise the electrode to cause the electrochemical reaction to happen. Electrochemical reactions start happening at the interface, and these reactions change the concentration ratio of products to reactants. This creates a concentration gradient between the bulk and the interface, and this difference in concentration at these locations, so this is a dCdx or concentration gradient, and so that drives flux to happen, namely diffusion. Let's take an example of the lithium-ion batteries, specifically the intercalation process. Once the lithium-ion batteries with lithium ions insert from the electrode-electrolyte interface into the electrode material itself, they then rely on the mechanism of solid-state diffusion to move from the shell of the electrode to the core. As the sites are actively filling during the charging process, lithium ions act as a semi-infinite diffusion. I like the one pictured here. The idea of semi-infinite may be new to some EIS users, but the idea is that an ion's movement is not restricted or influenced by its bounds. Eventually, in the case of these electrodes, when they're fully populated or fully charged, there's no more space, so it becomes blocking. We see this in thin layer electrochemistry also, and we'll call this finite diffusion. This type of diffusion will drive a different EIS response, which is valuable because it means that I can use EIS as a tool to investigate the diffusion process, remembering that we can do so at lower applied signals than comparative DC techniques. The time scale or time constant in this process means it is typically going to be probed or studied at low frequencies. As an electrochemist, I'm going to study electrochemical cells, though. I'm not going to study simple passive electronic elements. So let's take what I've learned about resistors and capacitors, inductors, and diffusion, and let's start building them together with some theory behind my electrochemical cell. Then describe how these experiments are performed and how the data are analyzed. Here I have 3 component circuits, and in the specific arrangement, this specific arrangement is called a Randall cell. The Randall cell is a resistor that is in series with an RC resistor capacitor network that are in parallel. The first resistor in series, shown as R1, is commonly used to characterize the equivalent series resistance, of which the solution resistance is a key contributor. Next, the resistor R2 that is in parallel with the capacitor C1 is used to characterize the study of charge transfer resistance or resistance to the Faradaic reaction. The capacitor C1 represents a double layer of my electrode-electrolyte interface, and as you can see with the Randall cell, then is the building block for a lot more complicated cells, as virtually every electrochemical cell is going to have some form of solution resistance, some form of charge transfer resistance, and have some double layer established. So let's look at the impact of frequency as the electrons try and flow through the circuit to predict where I'm going to see different information. We can start at the high frequency scenario. Electrons are going to first flow through that solution resistance R1 and then reach the branch of the parallel RC circuit. At that point, I can go up through the R2 resistor, or I can go down through the C1 capacitor. How does the electron decide which way it's going to go? It makes that decision based on frequency. When I get to that branch, remember that the inverse relationship of impedance of a capacitor to frequency. At high frequency, the impedance of the capacitor is low, therefore C1 acts like a short. And the electron shoots through the resistor R1 straight through. as if the capacitor is not even there. The impedance represents the value of R1 in that state. As I step the frequency lower and lower, the impedance of the capacitor changes. In the other extreme example of very low frequency, the impedance of the capacitor is very high. So my electrons are, after flowing through R1, it reaches a parallel network and it's forced up through the passive least impedance, which is now through R2. At that frequency, the measured impedance of the system is a combination of resistors in series, R1 plus R2. This gives me a method to identify what starting value to assign R1 because of the high frequency, and then R2 at low frequency would be R1 plus R2, so I can solve to get R2 now that I know R1, and we can use mathematical programs to approximate and fit the values for the capacitor. There's some graphical methods we can use to make the approximations of capacitor values as well. These data are plotted in two different representations, the Bode plot or Nyquist plot. The Bode plot on the left, the x-axis is the log frequency and the y-axis is the log of z or log of impedance magnitude. You often see this graph with phase on the y2 axis or on a separate graph. The Nyquist plot on the right, there's equivalent data, but that's important to understand. This equivalent data is shown here just in a different representation. So it is two ways to look at the same data. Here we'll see a z double prime versus z prime, or z real versus z imaginary. Let's look at these plots. The highest frequency give the lowest impedance. This is the far right of the Bode plot and the far left of the Nyquist plot. We compare the impedance values at the high frequency and we see both are approximately 10 ohms. Again, this is the first approximation of how much solution resistance or how much equivalent series resistance is in our system. As the frequency increments to a lower value in the Bode plot, you start to see picking up this -1 slope relationship on the magnitude, and that is a transition from seeing the influence of the capacitor on the last slide. Then down to the low frequency, we can see we have transitioned again to a pure capacitor. This is R1 plus R2. We see approximately 100 ohms in charge transfer resistance, since R1 plus R2 is 110 ohms. I get the question often, why is in the middle frequency the phase is not 90 degrees? But remember, for a Randall cell, this frequency, it's a mixed response of a resistor and a capacitor. It's not just a pure resistor. Next, you'll see the data on the Nyquist plot. I'm going to use the next slide to kind of walk you through that representation. So let's take some different electrical components and consider the representations on the Nyquist plot. First, what does the impedance of the resistor look like on the Nyquist plot? Since the resistor does not have any phase shift, then there's no imaginary impedance component. And remember, there's no frequency dependence either. So the resistor on the Nyquist plot would be a single point, and it would be on the real axis, the x-axis, and it's going to be representative of the value of R. When we look below, we can see the relationship of a capacitor on a Nyquist plot. Here with decreasing frequency, you can see the relationship would be a vertical line of a pure capacitor on the Nyquist plot. Note the impedance is all imaginary with no real component. And just I'll take a minute and tell you if it's an inductor, it'd be the same but opposite relationship. So similar relationship, but it would go straight down instead of straight up. So now let's look at that resistor and capacitor, and let's connect them together now in series. And you expect to see the vertical line from the capacitor, but it's going to be offset by the value of the resistor R1. Finally, at the bottom right, we can take this relationship and build on it further and see the Nyquist plot for the Randall cell. Now I have R1, R2, and C1. You can see at high frequency, I'm going to have R1. At low frequency, I'm at the combination of R1 plus R2. Therefore, the diameter of the semicircle is the value of R2. With the impedance of going from all real, picking up some imaginary influence, and returning to all real, that is the part that dictates that kind of semicircle type shape that we're familiar with seeing with Nyquist plots. So let's continue to build as we take what we've learned and look how data are typically modeled as the real cell. Here's a Nyquist plot that we've acquired on a lithium-ion battery from a BlackBerry cell phone. As discussed earlier, the response of an inductor is opposite to that of the capacitor. It's basically flipped over and into a different quadrant, and is expected at high frequency due to the reasons discussed earlier. We've taken this EIS response and built an equivalent circuit model shown over here on the right, and we use software to fit these different parameters. We can see the inductive component here by the value going below the x-axis, over to a time constant RC, represented by one RC network and then another RC network. These fits are mathematical operations used to assign values to the elements within our equivalence circuit. We can look at the literature for great reference guides. We can also start from our physical or chemical processes and the information delivered here to construct these electrochemical models. Here's another example of an energy device, a solar cell. It demonstrates the ability to measure 5 different regimes in a single experiment. We gain insight into series resistance, cathodic kinetics, porous electrode or transmission line, and all the way to recombination and into the diffusion limited response. We're going to get all this information in a single experiment with a relatively low stimulus. I'm going to be able to separate out these contributions and assign them representative values that relate back to different physical processes within the cell. And I can do that because of the different frequency dependence of them all. The parameter selection for experimental design of EIS can be relatively straightforward. The usual needs to make 2 key choices, however: control mode and signal amplitude. The control mode of most tests of energy devices are done in galvanostatic or current control mode. This sets the signal as the current, the response as the potential. If we carry that over to impedance, the relationship should be independent of control mode. So the first advantage that we get by eliminating the switch from current control to potential control back to current control unnecessarily. Another practical advantage is that potentiostats or battery analyzers have more current ranges than voltage ranges, and that's going to typically drive improved resolution and accuracy, as well as offsets of this control. Then with a sample of unknown impedance, it is a lot easier to prevent overloads. Whether we choose to execute our EIS experiments in either voltage control or current control mode, we need to be thoughtfully consider the amplitude selection. While we discussed that linearity should provide our ability to adjust our test conditions based on our sample, the selections are not infinite. We saw that if we drive a system too far, it will have a nonlinear response. But in low impedance devices, such as energy devices, there's also a danger of overloading the system. I advise that 10 millivolts is often selected as a default signal level, but consider a device that has a commercial battery for an application like an electric vehicle. This may have an impedance near or even less than 1 milliohm. If you have a 10 millivolt signal on a 1 milliohm load, it's going to generate plus 15 amps. So we're going to address this additionally on the next slide. But again, linearity suggests that you drastically reduce that signal level. However, we'll have a practical nature of some system design. Even with the superior design, components, calibration, it's very difficult to make high quality measurements below 1 millivolt. Remember that that's the RMS value of the wave, which means it's really on the order of like 10 microvolts or so, peak to peak in that assigned wave of 1 millivolt. Talk quickly about the bandwidth of the system. During material development, impedance measurements may go to a higher frequency into the hundreds of kilohertz or even the megahertz region. And when we think about something at that speed, the entire system has to be able to respond quickly. So how can we determine or characterize how quickly a system is going to respond? It's going to go to be a function of the potentiostat being used, the cell cable being used, the connections, and the cell being measured together, all working together because they all have an influence in how fast they respond. Bandwidth can be limited by the IDE converter, which is where the potentiostat measures current. If you're using a low current range, if a low current range uses a high current measurement resistor, and that high current measurement resistor goes with the capacitance on the board or the cell cable and make it RC time constant, so you'd be limiting the bandwidth of your potentiostat. The rise time of your control amplifier could be limiting the bandwidth. Your high impedance reference electrodes could also be limiting the bandwidth. But it's important to consider your system may need additional instrumentation to make the measurement required. In our example earlier of potentiostatic EIS generating a high current on a low impedance sample, a solution suggestion may be to use a current booster. However, current boosters are not ideal at devices either. They will have their own limitations on accuracy and resolution. They are additive to that of the potentiostat, and they also limit the bandwidth of the system. We can see an EIS measurement on a 100 milliohm resistor taken at 2 different systems. As we've learned in detail, the impedance of that resistor should be And so here we expect it to be 100 milliohms flat across the entire frequency spectrum. With the red plot, I get pretty much that, and that's using a galvanostatic EIS with a high current potentiostat, no booster, and so it's going to have faster bandwidth. What you see on the blue plot then is the same cell tested with EIS through an external booster, so a potentiostat requiring an external booster to raise the current level or signal level to make these measurements. And you can see below 2 kilohertz, we measured 100 milliohms. As I go to higher and higher frequencies, you see the impact of what we call roll-off, and you see that in signal level, or the impedance value rolls off and deviates from the expected value. I promise you a little bit more advanced EIS discussion over the next 2 slides. One technique is called harmonic analysis. It's a useful tool to determine the appropriate signal level that you can and should apply during EIS testing. So again, if the signal is too high, our response is going to be nonlinear, and the signal is going to be too low, my response is going to be noise dominated. So how do I do this? Well, over on the left-hand side, I have the same graph as we showed in the Butler-Vollmer slide to dictate or demonstrate linearity. Now I'm looking at a value that is further away from the open circuit voltage, and it's not now a nonlinear relationship. The graph on the right is data from a single frequency experiment of 180 hertz with a large stimulus applied. So I get a nice AC wave being applied at the cell at that frequency and get that response. But it's not uniform, and it's no longer a sine wave of current. This indicates that I am in a nonlinear region. And so how would I know that? Well, if I oversample the data, performed a FFT transformer of the data, which you'll see from this nonlinear data is a peak in the amplitude versus frequency graph and a peak at the applied frequency of 180 hertz. And you start to see the harmonics are every 180 hertz, so 360 hertz and 540 hertz. You'll see these frequencies, we get 2x the frequency and 3x and 4x and 5x. So you start seeing these harmonics drive out. The presence of those harmonics in a harmonic analysis would tell you the signal you applied is too large because we're picking up this nonlinearity. Between the harmonics, you'll also see what's basically a noise floor. We want to be sure that our response at that applied frequency is large enough above our noise floor that we can confidently say we're measuring that response with high quality. Harmonic analysis is an advanced tool. It's going to allow you to understand what you're seeing in a nonlinear region or a linear region. And most electrochemical impedance spectroscopy measurements test our desire to be ran in the linear region. There are a small subset of material studies that do benefit or it's active area research and intentionally nonlinear analysis. We talked a lot about stability of your system, and we talked about this, well, who wants to know, what do we want? We want to speed up our EIS plots. So EIS testing can be very long duration, as we talked about, and often driven by the lowest frequency being measured. But really everyone wants to test EIS faster. There's researchers that need to study low frequencies, such as diffusion control processes, specifically intercalation of these batteries and samples that are active. Both experiments that really benefit from the ability to speed up the total EIS duration. And so we can employ this technique called multi-sign EIS. We're going to use the principles of harmonic analysis we just talked about to really mix and apply different frequencies of the AC wave as possible. Up here on the right, or up here on the graph, we see 31 different sine waves that can be added together and applied to your system simultaneously. In doing so, you can see that we have a 5x duration improvement with functionally the same data. The ability to apply a very complex waveform to your system and extract all the data back out at different frequencies allows us to drastically decrease the total test time to where it is noise dominated, where it's dominated by the single, where the time is dominated by the single lowest frequency instead of successive points all the way down to the lowest frequency. These pictures and labels describe how auxiliary electrometer technology can be applied as we stack these devices together in series for stacks or modules. Current is the rate at which electrons flow through the device. For a connected stack of cells, the current is the same in every location. With impedance being the ratio of voltage to current, the position of the voltage measurement dictates where the reported impedance is measured across. Multiple voltage measurements give simultaneous measurements of impedance, at different positions in the stack. This requires matched coordinated measurements from voltage inputs of the auxiliary electrometers. At the material or cell level, this identifies if the anode or cathode is dominating the cell impedance. At the stack or module level, this identifies if a single cell is dominating larger impedance. Making this determination leads us to failure analysis and helps us direct research or replacement. We can look at a method to understand accuracy of EIS measurements. Energy devices are low impedance devices by nature, and our goal may be quantitative results or qualitative trends. So it is important for us to understand the capability of our system that is being used by test. By connecting to a passive cell with a well understood ideal response, we can compare the measured data to those expectations. When these data are run over a range of impedance and a range of frequency, we can build a map to define our expected accuracy. So here let's go through and show a couple examples of EIS being used for diffusion at diffusion at the material level and state of charge and state of health measurements. Here we can see on the top left, we're going to see a classic system or a typical Nernstian type response for EIS. And we see that we have the kinetic control at high frequency down to mass transfer control at the lower frequencies. This is a semi-infinite type diffusion. You see something barely similar in a degrading lithium-ion battery, but as it degrades, what happens? The impedance grows, so the whole figure shifts to the right, and you see that we have some inductive behavior that we don't see in the classic response, and you can see that we've picked up a second RC circuit due to that SCI layer. Bottom left-hand corner, let's look down and we can see kind of a semi-infinite diffusion response for lithium-ion batteries as they continue to insert and diffuse all the way over to a finite diffusion, or as after all the interstitial sites are filled, and you can see that kind of transition from a semi-infinite diffusion up to a finite diffusion response, or as it looks more capacitive because all of that is filled. So the flat voltage profile or plateau of a charging or discharging lithium-ion battery gives the cell a lot of its attributes. However, it means we need a more sophisticated method to measure state of charge. So I took a commercial 18650 cell to our lab and measured its impedance when fully charged, then discharged it by 10% of its capacity and measured its impedance again, and then repeated that until the cell was completely discharged. These plots are overlaid and presented here. We can see that this creates statistically different results. We're still looking for small changes in small numbers, so the theme of accuracy and resolution are important. And we see the biggest shift is at the high impedance, which is measured at low frequencies, and that's what we talked about in Randall's slide cell. So with this series of experiments, we've created an impedance-based sensor for state of charge of lithium-ion batteries. Another way to do this, we can take this with our VersaScan electrochemical scanning electrochemical workstation, and we can map this very similar type of experiment, but now map it with another dimension, and that dimension of position or space. And what that's going to do is allow us to create data maps as we take the local impedance at different locations, and we can watch and see how the state of charge is different within our battery by position of measurement. So time constant is a product of R in ohms and C in the value in farads, and thus units of seconds. EIS has been used to measure time constants as a function of state of health at different states of charge. At low states of charge, such as 20%, the impact of state of health is more easily measured, as the impedance is larger and more easily characterized. However, we can discern this up to 90%. The EIS can determine state of charge at a given state of health or state of health at a prescribed state of charge or temperature. This relationship of EIS to state of health is based on more than a single parameter. This result is critically important, and we're going to spend the next slide talking about the economic opportunity kind of associated with this. But in general, we can say if we look at this, we can see the top left, we're going to see that you have a new battery, an aged battery, and you can see this is from Nissan, a module from a Nissan Leaf battery, and you can see this bit of an offset. Down here on the left and right, this was taken on smaller cell batteries, but we can see that the state of health of the battery decreases rapidly as the battery is being used, and then the data correlating that with a given state of charge back to or given impedance data showing their relationship to state of health at given states of charge. So we can take that and kind of build on that, and through a consortium that AMETEK was a part of with Nissan, with WMG, with Element Energy, and with the UK EIS funding. What we were able to show is by taking Nissan modules, top left, we take an impedance spectrum of Nissan module. If we take enough of that data and acquire it at different states of charge and different temperature, we can build a sophisticated algorithm that's going to take that state of charge and temperature into account. And by doing that, we can build a data analysis algorithm that allows it to be applied and rapidly grade these state of charges and rapidly grade these modules at different states of charge and different temperature. And so what that's going to allow me to do is take measurements much more quickly, as we said, but not having to set a temperature and set a state of charge. And those are big sinks in time and energy. So being able to avoid those are very important. I'd love to tell you more about that if you want to contact us to speak about that further. So final review, we have some key concepts. Processes occur at different rates. Thus, using frequency domain techniques such as EIS, we can separate these out from different electrochemical processes. In general, fast processes like electrokinetics are studied at high frequency, and slow processes like diffusion are studied at low frequency. EIS can determine the total individual mechanism's contribution to the characteristics of the cell in a single experiment. And this allows us to do a lot of different things like fault analysis and study state of charge of batteries and state of health and diffusion. Well, thank you for your attention and time today. This does conclude today's conversation. Electrochemical impedance spectroscopy testing theory is a technique in some ways is being used as research and scale level needs continue to have challenges and opportunities for lithium-ion batteries. Thank you and have a good day.